Hello, everyone. It's my pleasure today to present to you my executive summary of my thesis work, which will give you the information that the incorporating a 3D point source will have a positive impact in the processing steps, including deghosting and the multiple removals for 1D subsurface data. Here is the seismic tree studied by our group, and this project aims to improve the effectiveness in deghosting and to multiple removal processings by adding the realistic source dimension, which we assume is a 3D point source dimension. On the left-hand side here, I extracted several key processing steps from the previous tree and make it a simpler tree here. And we can see that these highlight parts are the processing steps are covered in this thesis work. And I would like to point out that all the steps here are isolated tasks. These isolated tasks are accomplished in sequence, which means each step is after each step is achieved, the problem in the next step will restart without going back. So improve the effectiveness in each step is really important for the subsequent processing here. Speaking of improving the effectiveness, we always want to involve more realism in our assumption. One of the realism is the source dimension. So here we would like to point out it's more realistic to assume a 3D point source in processing rather than a frequently used 2D line source. So the challenging here is that for the data coming from a 1D subsurface, which is a reasonable assumption for many circumstances like Central North Sea, 1D Earth algorithm frequently starts with a 2D algorithm, which assumes a 2D line source in it, and then reduce the Earth dimension from 2D to 1D. So in this reduced algorithm, the source dimension assumption is 2D line source. This thesis work, what will we show in this talk? We start with a complete 3D algorithm, which assumes a 3D point source in it, and then reduce the Earth dimension from 3D to 1D. So that in our reduced algorithm, we still assume carries the assumption of a 3D point source. And also, this work will show you the significant difference between the processing methods assuming a 2D line source versus a 3D point source for the data actually coming from a 3D point source and 1D subsurface. I can summarize my thesis work by this chart here, and basically we incorporate the 3D point source in the deghosting method for 1D subsurface in this year, and this part has been shown in yesterday's talk. And the second part is we incorporate the 3D point source in the SS free surface multiple removal methods for a 1D subsurface data, which will be discussed and shown the results to you in this talk. And for also we incorporated this 3D point source for the next step, which is the internal multiple removal for both the 1D and the 2D subsurface data. The conclusion from that part is similar to the conclusion we will draw in this talk. So this part will not be discussed in details in this talk. But if you are interested, I refer you to my reports in 2014 and 2015. So in this talk, we will focus on the topic which is which test is remove the free surface multiple in your data. So we incorporating a 3D point source in the ISS free surface multiple elimination algorithm for 1D subsurface. This algorithm is pioneered by Carvalho et al. al in 1992 and Wiglan al in 1997. In principle, this method can provide you the perfect time and the perfect amplitude of free surface multiple. So through a basic subtraction, direct subtraction, you can eliminate the free surface multiples in your data. The contributions of this from this work to current as free surface 3D source free surface multiple elimination algorithm for 1D subsurface is: first, we reduce the data requirement from an area coverage of all the receivers to only one line coverage of all the receivers. The second is we improve the effectiveness of the free surface multiple prediction by assuming a 3D point source rather than a 2D line source for the 3D point source data, which we consider as the more realistic data. So next, I will show you numerical tests. These tests are designed for show you the significance of incorporating a 3D point source. So in this test, we will show you the difference between the SS free surface multiple elimination prediction and removal result by assuming a 2D line source versus a 3D point source for the data coming from a 3D point source. So this chart here gives you a basic idea of this test. When we see our data always comes from 3D point source, but in our processing, we can assume a 2D line source as we frequently people usually do, and we call this kind so that the assumption of the source dimension in your processing disagree with the source dimension in your data. We call this mismatch. And our work is we incorporate this 3D point source in the processing, and that the source assumption in your processing agree with the source in dimension in your data. So we call it a match here. First, let me show you the synthetic 3D point source data we generated for the test. Here is the model we use to generate the 3D point source data. This is a velocity density various model, and the source location and the cable location are presented here, which contains 3 reflectors, 4 layers, and for the data generation, we assume we generated deghosted data, which means in our data there is no ghost and direct wave. So this slide shows you the 3D point source input data we generated by the model we just showed you, which does not contain the ghost and the direct wave. In this data set, we have 3 primaries: first order free surface multiples, and the second order free surface multiples. And the other events are the internal multiples. Compared to these 2 kind of events, internal multiple events are too weak to be seen. So we are not label them out. Since in this data set, we have the free surface multiples up to second order. So in the later processing, we will use the SS in free surface multiple prediction and the removal up to the second order. In principle, this method can eliminate both the first order free surface multiple and the second order free surface multiple. But we will see the different assumption of the source dimension will give you very different result. So let's move to the SS free surface multiple removal processing. The first test, I assume, as we usually do, I assume 2D line source in the processing. rather than a 3D point source. Here we mismatch the source dimension in the processing and the data. Again, this figure shows you the data set we use as input. And this figure shows you the free surface multiple removal method, removal result, assuming a 2D line source which mismatch the source dimension in your data. This result, we flip back and forth, we can hardly see any reduce of the free surface multiples. In other words, serious free surface multiple residuals exist in your output data after the subtraction. So, why this 2D line source free surface multiple removal method gives us such a significantly less effective result? To explain this problem, I will show you one trace plot at a fixed offset to explain. First, let me show you by this solid red line here. This solid red line represents the original 3D point source input data. This is our data at the 200 meters offset. And we labeled all the free surface multiples. We know since it's a synthetic data, label them out by these arrows. And we can see, please notice that we plot this trace in the in this scale, which is 10 minus 5. Next figure, I will show you the 2D line source as free surface multiple prediction, which means we mismatch the source dimension in the processing, and I will show the prediction trace, not the trace after the subtraction, by this blue dashed line here. We can see that when we plot them in the same scale, plot them together here, this prediction looks flat. It looks like a zero trace. So you may ask, does this 2D line source free surface multiple prediction fails because of we mismatch this source dimension? The answer is no. When we change this plot scale from 10 minus 5 to 10 minus 7, which is 100 times smaller, then replot this 2D line source free surface multiple prediction out, then we can see the predictions are here. But this kind of prediction carries the amplitude 100 times smaller than the original data, which is a significantly less effective prediction. Using this kind of prediction, subtract this kind of prediction from our data, we will have this dashed black line here. The dashed black line actually is very close to our data set, which means the internal multiple, the free surface multiples in your data set cannot be effectively reduced. The severe free surface multiples exist in your data after the removal. Okay, let's move to the 3D point source processing, which means we incorporating a 3D point source in our free surface multiple elimination algorithm. Then we process the 3D point source data. That two source dimensions are matched to each other. So again, this figure here shows you the 3D point source input the data we use to we use as the input. And this figure shows you the free surface multiple removal result, assuming a 3D point source. We can flip back and forth. We can see that all the first order and the second order free surface multiples are eliminated. They are gone, completely gone, because we correct this source dimension in our processing assumption. And this kind of effect, this kind of difference can also be found in the ISS internal multiple removal method. And the conclusions are similar. If you are interested in the internal multiple removal by improving internal multiple removal by incorporating 3D point cells, I refer you to these two reports. So at the end, I would like to draw the conclusion here. The reduced 3D point cells 1D subsurface algorithm, including free surface multiple illumination and internal multiple attenuation algorithm, can work for one-shot gather at one time with a line coverage of receivers. And the reduced algorithm incorporating 3D point cells provide effective results, as we seen before, completely remove the free surface multiples, as a complete 3D algorithm can produce to us for the data coming from 1D Earth. And the last point is applying a 2D line source algorithm on the 3D point source data, which means we mismatch the source dimension in our processing method, can generate a significantly less effective prediction, which will make your which will generate issues in your subtraction after the multiple removal. Thank you. That's all. Thank you.